Welcome back to the deep dive. I want to start today by asking you to just visualize something for a moment. It's an image that I think most of us have carried around since we were kids in school.
Oh, I know this one.
I want you to picture the solar system.
It's the classic mobile, isn't it? The one hanging over a crib.
That's the one. Or maybe that styrofoam model we all, had to build for the science fair in fourth grade.
Right, with the coat hanger wires and the little painted balls.
Exactly. And in that model, everything is just perfect. You have the sun in the middle, this big, glowing, static yellow basketball. It's not doing much, just sitting there.
And then you have the little planets all politely circling nearby.
In their assigned lanes, right. The little rocky ones, Mercury, Venus, Earth, Mars. Then there's the asteroid belt, which is this, nice, tidy divider.
A very neat little fence.
A fence, yes.
Right.
And finally, on the other side, you have the big guys, the gas giants, creating these majestic, slow, perfect circles on the outside.
It is a very comforting image.
Yeah.
It looks like a clock. It ticks. It's predictable. It's orderly.
Right. It feels permanent. Like, this is how it was, this is how it is, and this is how it's always going to be. But the source material we're unpacking today, a really dense and fascinating transcript from the channel SEA called The Birth of the Solar System. It basically takes that clockwork model and just smashes it with a sledgehammer.
Smashes is definitely the right word. Because if you actually look at the history, the solar system isn't a museum exhibit. It's more like a crime scene.
A crime scene, that's a strong way to put it.
I think it's an accurate one. The neat, orderly arrangement that we see today is really just the aftermath. It's what's left over after a violent, chaotic, and incredibly dynamic history.
So planets didn't just pop into existence where they are now.
Not even close. They didn't just gently form in their current spots and stay there. They migrated. They hunted each other. They smashed into each other. They literally starved each other of the material they needed to grow.
And that is our mission for this deep dive. We are going to try and reconstruct that timeline. We're going to go from a giant cold cloud of gas all the way to a scenario that I have to say I think is going to floor a lot of you listening.
I think so, too.
The source makes a really compelling case that at one point, our system didn't just have one habitable world. It potentially had 3 blue planets capable of supporting life.
That's the part that always gets me, the what could have been. We're going to look at those make-or-break moments. Because the difference between Earth, which is this thriving oasis, and our neighbors, which are essentially planetary graveyards, it really all comes down to a few critical, almost random twists of fate in that early chaos.
So let's start with what the outline calls the neighborhood watch. Before we blow it all up, we should probably define what the territory looks like right now. But let's go a little beyond that 4th grade model.
Right.
What are we actually looking at when we talk about the solar system in its entirety?
Well, okay, so if we take a snapshot of today, the system is about 4.5 billion years old. You've got the inner system, that's us, the terrestrial planets.
Right. Mercury, Venus, Earth, Mars.
We're the rocky midgets, basically, huddled close to the fire.
Rocky midgets, that's charming. Yeah. Okay, so we're the rocky midgets.
Yeah.
And then you go past the asteroid belt.
You hit the giants, and we should probably distinguish here because they're not all the same. Jupiter and Saturn are the gas giants. They're these massive balls of mostly hydrogen and helium. I mean, they're basically tiny failed stars in their own way.
Okay, so they're almost all gas.
But Uranus and Neptune, the ones furthest out, they're actually a different class. We call them ice giants.
Ice giants, so they're just frozen solid.
Well, it's a bit of a funny term. They have a lot more heavy volatile elements, things like water, ammonia, methane, which astronomers just call ices, even if they aren't, frozen solid like an ice cube. It just means they're not primarily hydrogen and helium. They have more substance to them.
But the map doesn't end there, right? It doesn't just stop at Neptune. This was something the source material really emphasized, and I think it's something most people just completely miss.
Yeah.
The solar system is exponentially larger than just the planets.
Oh, much, much bigger. If you stop at Neptune, you're basically stopping at the front porch and completely ignoring the rest of the estate.
So what's out there in the yard?
Beyond Neptune, you enter the debris fields. First up, you have the Kuiper Belt. The easiest way to think of it is as a much larger, much icier version of the asteroid belt.
Okay, so more asteroids, but icy ones.
Exactly. It starts just past Neptune's orbit and extends out to about 55 astronomical units.
And just to ground us a little, an astronomical unit, or an AU, that's the distance from the Earth to the Sun. So we're at 1 AU.
Right.
So the Kuiper Belt goes out to 55 times that distance.
55 times, yeah. And even that is just the beginning. Beyond the Kuiper Belt, you have what's called the scattered disk, which goes out over 100 AU.
What?
And then way, way out there, encompassing everything, you have the Oort cloud. This is a hypothetical massive shell of icy debris that wraps around the entire system like a bubble.
The scale here is just, it's really hard to wrap your head around. The source used an illustration that really stuck with me to try and explain just how big this Oort cloud is.
The light speed comparison.
Yeah. So light is the fastest thing in the universe, right? It takes about 8 minutes for light to travel from the sun to us here on Earth, which is pretty fast.
Use that, yeah.
But to get from the sun to the outer edge of our own solar system to the edge of the Oort cloud,
It takes more than 18 months.
18 months traveling at the speed of light. That is just a terrifying amount of empty space.
It is. It really isolates us. And for a long time, because our system is so big and on the surface so neatly arranged, small rocks inside, big giants outside, we assumed this was the standard model for the universe. We thought, okay, this is just how physics works. This is how planets form. It must be universal.
But then 1995 happened, and the universe essentially told us, no, you guys are actually the weirdos.
1995 changed absolutely everything. That was the year we confirmed the first exoplanet orbiting a sun-like planet called 51 Pegasi b. And when we looked at that system, and then at the thousands of systems we found after it, we didn't find these neat little clockwork models like ours.
What did we find instead?
We found absolute madness. We found hot Jupiter's gas giants orbiting right next to their stars, closer than Mercury is to our sun. I mean, imagine a planet the size of Jupiter where our Mercury is.
The heat would be unbelievable.
Unbelievable. We found planets on these wild elliptical orbits that swing way out into deep space and then dive-bomb their stars. We found systems that look like they had been put in a cosmic blender.
So the big realization was that planets don't just stay put. They're not on fixed tracks.
Exactly. We realized that planetary systems are naturally dynamic. They migrate, they drift. And that realization forced astronomers to look back at our own history and ask, wait a minute, if everyone else's planets are moving around, did ours move too?
And the answer, as we're about to see, is a resounding yes. But to understand the movement, we have to understand the birth. We have to go back to before there was an Earth, before there was even a sun. Let's go to these cosmic nursery.
Right. So everything you see around you, I mean, the water in your glass, the iron in your blood, the silicon in your phone, it all starts in what we call a molecular cloud.
Okay, what is that?
Imagine a colossal cloud of gas and dust in deep space, maybe 65 light years across. It's incredibly cold, just a few degrees above absolute zero, and it's mostly just sitting there.
And it's mostly hydrogen, right? The simplest element.
Mostly hydrogen and helium, yes, but it's seasoned with trace amounts of dust. And when astronomers say dust, they mean tiny particles of silicates, organic molecules, basically the building blocks of rocks and life.
Now, I think we often imagine the sun forming in this lonely isolation in the dark, just one star popping into existence in the middle of nowhere.
That's the romantic view, for sure. But the source material points out that it's almost certainly wrong. The sun was not an only child.
We have siblings, like star sibling.
We had a whole family. The source suggests the sun formed in what's called a solar birth cluster. We're likely talking about 200 to 400 sibling stars, all forming from the same massive cloud at roughly the same time.
That is a wild thought. If we could stand on a planet 4.5 billion years ago and look up, the night sky wouldn't look anything like it does now.
No, it would have been dazzling. You wouldn't see constellations. You'd see this brilliant cluster of hundreds of bright, nearby stars, our brothers and sisters.
So what happened to them? Where did they all go?
Well, gravity is a fickle thing. Over hundreds of millions of years, as this whole cluster orbited the Milky Way, the family just drifted apart. They're all out there somewhere now, anonymous stars in the galaxy. But we started as a group project.
So you have this cloud, it's cold, it's massive, but clouds are usually pretty stable. I mean, they're just gas. What actually triggers it to turn into a solar system? Why didn't it just stay a cloud forever?
You need a spark. A cloud like that needs a kick to start collapsing. Gravity is there, of course, but it needs a nudge to overcome the internal pressure of the gas pushing outwards.
And what was our nudge?
The smoking gun evidence, which we find in our oldest meteorites, points to a supernova.
A supernova. So a star exploding nearby.
A massive star, somewhere in our stellar nursery, reached the end of its life and detonated. That explosion sent a shockwave cascading through space. When that shockwave hit our molecular cloud, it did two critical things.
Okay, what's the first one?
First, it slammed into the gas, causing it to compress and, crucially, start rotating. That's the kick that started the whole gravitational collapse. Without that spin, it would just fall into a black hole. You need the spin to form a disk.
And the second thing?
It salted the soup. The explosion showered our cloud with heavy elements materials that were forged in the heart of that dead star. Elements like iron, gold, platinum, uranium.
Wait, I want to pause on that for a second. So the gold in a wedding ring, that didn't come from our sun.
Not at all, no. Our sun acts like a giant nuclear fusion reactor, but it's mostly just fusing hydrogen into helium. It can't make the really heavy stuff like gold or uranium. That material was delivered, prepackaged, by a dying star before our system was even born.
So we're made of the ashes of a dead star.
Literally. That supernova provided the raw materials that would eventually make up the cores of the planets and, everything else.
That is humbling. Okay, so the cloud is awake, it's spinning, it's collapsing. Now we enter what the outline calls the T-Tauri clock. And the way the source describes this, it sounds less like a clock and more like a time bomb.
It is a time bomb. It's a very, very strict countdown. So as gravity collapses this gas, it flattens into a spinning disk called an accretion disk. Think of it like a spinning pizza dough.
Okay.
And in the center, matter compresses more and more to form the seed of the star, the protosun. But for the first 100,000 years or so, it's not really a star yet. It's just a hot ball of gas getting squeezed by gravity.
It's not fusing hydrogen. It's not on yet.
Not yet. It's glowing from the heat of compression, but the furnace hasn't lit. But then it enters the T-Tauri phase. This is named after a specific variable star that serves as the prototype for this stage of stellar life.
And what's that like?
Think of this as the sun's adolescence.
And like many adolescents, it's violent and temperamental.
Extremely. The young sun starts erupting. It shoots out these twin polar jets of gas that go for light years into space. But most importantly for us, for the planets, it generates incredibly strong solar winds. It starts blasting radiation and particles outward in all directions.
And this is where the clock starts ticking. Why is this a problem for planet building?
Because planets are made of the dust and gas in that accretion disk. But the T-Tauri wind is actively blowing that disk away. It's cleaning house. It's like a giant leaf blower, pushing all the lighter gases out into deep space.
So if you're a planet, you have to form before your building materials literally get blown away into nothing.
Exactly. It's an absolute sprint. The T-Tauri phase lasts for about 10 million years. Now, that sounds like a long time to us, but in cosmic terms, it's a blink of an eye.
A very short window.
If a planet hasn't gathered its mass within that window, it never will. Once that wind blows the gas away, the construction site is closed. There are no more bricks to build with.
Wow. That adds a lot of stakes to this process. It's not just slow and steady wins the race. It's grab what you can before the solar wind blows it all into interstellar space.
Precisely. And this frantic rush to accumulate matter leads us to the next big chapter, the Great Divide.
This is the answer to the question I hear all the time.
Yeah.
Why are the planets so different? Why is Earth a rock and Jupiter a massive gas ball?
Right. Why didn't Earth just keep growing and become a giant?
And why is the split so perfect? You don't see gas giants right next to the sun in our system, and you don't see tiny rocks way out deep.
Yeah, it's like there's a rule. There is a rule. And it all comes down to temperature. We call it the frost line, or sometimes the snow line. In the early solar system, this line was located about 5 AU from the sun, roughly where the asteroid belt is today.
Okay, so help me visualize the physics here. Inside the line, closer to the sun, it's hot.
Right. It's too hot for volatile compounds like water, methane, and ammonia to exist as solids. They vaporize. They stay as gas.
So they can't clump together.
Exactly. The only things that can exist as solids, the only things that can clump together to form a planet, are rocks and metals. Silicates, iron, nickel.
And those are rare, right?
Yeah.
Compared to all the gas in the nebula.
Incredibly rare.
Yeah.
Rock and metal make up less than 1% of the nebula's total mass. So inside the frost line, the available building material was incredibly scarce. You were trying to build a castle, but you only had a few handfuls of sand.
So you could only build small things.
You could only build small things. That's why Mercury, Venus, Earth, and Mars are all relatively tiny. They were built from the scraps.
But outside that line, past the asteroid belt.
Outside the line, it's cold enough for all those volatiles, water, methane, to freeze into solid ice. And in the universe, ice is abundant. It's everywhere. So out there, the planetary cores could grow massive very, very quickly. They weren't just collecting rock. They were collecting vast amounts of ice.
So they got big fast.
They got huge. And this is the absolute key. Once a core hits about 10 times the mass of Earth, its gravity becomes strong enough to do something Earth never could.
What's that?
It becomes strong enough to trap hydrogen and helium gas directly from the nebula.
So they started eating the atmosphere of the nebula itself. They started vacuuming up the main ingredient.
Exactly. They started vacuuming up the gas before the T-Tauri winds could blow it away. They just ballooned into gas giants. Earth never got big enough to cross that threshold, so we stayed a rock. Jupiter crossed it, and it became a king.
So the temperature gradient of the solar system basically segregated the planets at birth. It was like a sorting mechanism. If you formed inside the line, you were destined to be a rock. If you formed outside, you had the chance to become a giant.
That's the fundamental rule. But as we're starting to learn, the rules in the early solar system were made to be broken. And the biggest rule breaker of them all was the king himself. Which brings us to the king and the chaos.
Jupiter.
Jupiter. It is the main character of the early solar system. It's not just another planet, it's the dominant gravitational force after the sun. Everything else is just responding to what Jupiter does.
The source material calls it the firstborn.
Yes. The models suggest Jupiter formed just beyond that snow line about 3 million years after the system started. It was likely the first planet to see the sunrise. And because it was first, and because it was in that sweet spot just past the snow line where ice was plentiful, it had an all-you-can-eat buffet.
It grew to 320 times the mass of Earth. That is a number that's hard to even picture. If Earth is a nickel, what is Jupiter?
If Earth is a nickel, Jupiter's a basketball. It's immense. But here's the twist that those 1995 exoplanet discoveries helped us understand. Jupiter didn't stay put.
This is the migration theory. I've heard it called the grand tack.
The grand tack model, right. So as Jupiter was gobbling up all the dust and gas in its path, the drag from the remaining material in the disk caused it to lose orbital energy. And as it lost energy, it began to spiral inward toward the sun.
Wait, can you explain that a little more? I always thought orbits were these fixed tracks. How does a planet just spiraling in?
Think about it like riding a bike through a shallow pool of water. The water creates drag, right? It slows you down.
Sure.
In orbit, if you slow down, you fall inward toward the center of gravity. Jupiter was plowing through this thick soup of gas and dust, and that friction was constantly stealing its momentum, causing it to migrate toward the inner solar system.
A wrecking ball moving through a construction site.
A perfect analogy.
Yeah.
Imagine this massive gravity, well, this basketball, moving inward, crossing the asteroid belt, and coming as close to the sun as where Mars is today.
Oh, wow. So what does that do to the inner solar system, to us?
It devastates it. As Jupiter moved in, it just plowed through the material it should have gone on to form Mars. It effectively starved Mars before it could even get going.
The source mentioned this. This is the leading theory for why Mars is so small, right?
It is, yeah. Mars is only about 10% the mass of Earth. Models suggest it should be bigger. It's in a pretty good location.
Right.
But Jupiter came in, ate its lunch, scattered the rest of the food all over the room, and left Mars with nothing but leftovers. Mars is a victim of Jupiter's hunger.
But Jupiter didn't crash into the sun. It didn't become one of those hot Jupiters we see in other systems. What stopped it? Why did it turn around?
Saturn. Saturn saved the day.
Oh.
Saturn formed a bit later than Jupiter and a bit further out. And it started migrating inward too. Eventually it caught up to Jupiter. When they got close enough, they got locked in this powerful gravitational dance, a resonance that actually stabilized them and reversed their direction.
So they kind of pulled on each other and stopped the inward fall?
Exactly. They tacked, just like sailboats turning into the wind, and started to move back outward together.
So Jupiter came in, smashed up the inner system, starved Mars, and then just left.
Pretty much. It retreated back to the outer solar system with Saturn in tow. But the damage was done. The inner solar system had been severely depleted of material. It's probably why we don't have any super-Earths like we see in so many other systems. Jupiter cleared them out before they could form.
Okay, so Jupiter heads back out. But it didn't just go back to peace and quiet. This leads us to the next big event, the grand reshuffling. And this seems to be the moment where the solar system went from being just somewhat chaotic to absolute madness.
This is the event that truly defined our current structure. It's the key to explaining the weirdness of the outer planets.
Specifically, Uranus and Neptune, right? The source calls them failed giants, which feels a bit harsh.
It is a bit harsh, but physically it's accurate. So Uranus and Neptune are weird. They're huge, but they're not Jupiter huge. And more importantly, they are currently sitting way, way out at 20 and 30 AU.
And that's a problem for the models.
It's a huge problem for the math. We talked about density. As you get further away from the sun, the gas cloud gets thinner and thinner. At 30 AU, where Neptune is, the solar nebula would have been incredibly thin. There simply wasn't enough material out there to build a planet that big in the 10 million years available.
So they couldn't have formed where they are now. It's impossible.
It would have taken longer than the age of the universe to build Neptune way out there. So the solution is that they must have formed much closer in perhaps between Jupiter and Saturn. They were part of a much more crowded inner club of giants.
So what happened? How did they get thrown so far out?
About 500 or 600 million years after formation, Jupiter and Saturn drifted into a new, very powerful resonance.
Explain that to me again, a resonance.
Okay, think of pushing a child on a swing. If you just push at random times, nothing really happens. But if you push at exactly the right moment, every single time the swing comes back, what happens?
They go higher and higher. You add energy.
Exactly. You are pumping energy into the system through rhythm. Jupiter and Saturn fell into a 2.1 resonance. For every one time Saturn orbited the Sun, Jupiter orbited exactly twice. Every time they lined up in their orbits, they gave each other a powerful gravitational shove.
And who paid the price for all that new energy being pumped into the system?
The smaller guys, Uranus and Neptune. This gravitational instability acted like a giant slingshot. It destabilized their orbits and hurled Neptune and Uranus outward away from the Sun.
Just threw them into the dark.
A violent eviction. And think about what was out there waiting for them. The ancient Kuiper Belt. Back then, it wasn't just a few scattered rocks like it is today. It was dense. It was absolutely packed with trillions of icy bodies left over from formation.
So Neptune is flying outward at high speed, and it hits this wall of debris.
It plowed into this field of icy rocks like a bowling ball hitting a full rack of pins.
Total chaos.
Absolute system-wide chaos. This debris, trillions of icy comets, was scattered everywhere. Some of it was thrown way, way out to form the Oort cloud we talked about, but a lot of it was thrown inward.
And inward means toward us.
Toward Earth, Mars, Venus, and Mercury. This event is what we now call the Late Heavy Bombardment. For millions of years, the inner planets were just pummeled by a constant rain of asteroids and comets from the outer system.
What would that have been like?
It sounds apocalyptic.
Yeah.
If you stood on Earth during this time, the sky would have been lit up constantly by impacts. It was a rain of fire and ice.
It sounds like the kind of thing that would destroy a planet, not help it. But the source mentions a silver lining to this bombardment.
It does. And it's a beautiful, beautiful irony. This violence, this apocalyptic event, is likely the reason you and I are here today talking about it.
Because of the water.
Because of the water. Remember, Earth formed inside the frost line. We started out as a dry, hot rock. We shouldn't have oceans. The water should have all vaporized and been blown away.
So where did all our water come from?
It was delivered. Special delivery. Those icy comets that Neptune flung at us during the bombardment, they were loaded with water ice. They smashed into the young Earth, melted, and over millions of years they filled the basins that became our oceans.
So the oceans we swim in, the rain that falls, that is all melted comet ice from the outer solar system, delivered during a planetary catastrophe.
A significant portion of it, yes. The very chaos that scarred the planet also delivered the single most important ingredient for life. We are essentially a dry rock that got hit by enough cosmic snowballs to create an ocean.
That is an incredible thought, and it creates a perfect segue to the segment I've been waiting for, the tale of 3 blue planets. The source revealed something that really shifted my perspective on this. We think of Earth as the blue planet, the unique one. But you're saying that wasn't always the case?
No, not at all. In the early solar system, after that water arrived from the bombardment and things cooled down a bit, it is very, very likely that we had 3 ocean worlds: Venus, Earth, and Mars.
All 3, with liquid water on their surfaces.
All 3. They all sat in or near what we call the habitable zone at the time. They all had solid surfaces. And they all received that massive water delivery from the late heavy bombardment.
So if an alien astronomer had looked at our solar system 4 billion years ago, they wouldn't have just seen Earth as the prize. They would have seen 3 potential homes for life.
Likely, yes. They would have seen a blue Venus, a blue Earth, and a blue Mars. 3 shining jewels.
So what happened? It feels like a horror movie where the characters get picked off one by one until only the final survivor is left standing. Let's start with Mars. We know it's a frozen desert now.
Mars is the tragedy of being too small. We know for a fact Mars had flowing water. We can see the dried up riverbeds from orbit. Our rovers are looking at rocks that were clearly tumbled in ancient streams. But Mars died of cold.
Why? What does a planet's size have to do with its temperature?
It's all about the core. A planet's magnetic field is generated by a spinning molten metal core dynamo. That field is absolutely crucial. It acts like a protective shield, deflecting the solar wind.
And the solar wind is that stream of radiation from the sun we were talking about earlier.
Right. It's a constant stream of charged particles moving at 1,000,000 miles an hour. If it hits an atmosphere directly, without a shield, it just strips it away. It physically knocks the air molecules out into space.
So Mars had a shield at one point.
Initially, yes. But because Mars is so small, remember Jupiter starved it, it has less internal heat. Think of it like a small cup of coffee cooling down much faster than a big pot. Its core cooled down and solidified much faster than Earth's.
And when the core solidifies, the dynamo stops, the shield goes down.
Exactly. The magnetic field turned off. And suddenly, the full force of the solar wind was hitting the Martian atmosphere directly. It started stripping the air away. As the atmospheric pressure dropped, the water on the surface couldn't stay liquid anymore. It just evaporated and was lost to space. Mars suffocated in the cold vacuum.
How long did it have as a blue planet?
The estimates are maybe a few 100 million years. Just enough time for life to maybe get started, which is why we are so desperate to search for fossils there. But not enough time to sustain a complex biosphere.
Okay, so Mars froze to death because it was too small. What about Venus? Venus is big. It's almost the same size as Earth. Its core didn't cool down too fast.
No, Venus had the exact opposite problem. Venus died of heat. But for a long time, it was probably quite nice. Models suggest it had shallow oceans for potentially up to 2 billion years.
2 billion years? That's almost half the age of the solar system. Life could have evolved significantly there.
Absolutely. It had a huge window. But it was ultimately doomed by the sun itself.
How so?
As stars like our sun age, they get brighter and hotter. It's a very slow, gradual process. But over billions of years, the sun turned up the thermostat on the whole system. Venus, being closer to the sun than we are, eventually crossed a critical tipping point.
The ocean started to boil.
And here is the mechanism that killed it, which is a terrifying lesson for us. Water vapor is a greenhouse gas, a very potent one. So as the oceans began to evaporate due to the rising heat, the atmosphere got filled with more and more steam. That steam trapped more heat, which caused more evaporation.
The runaway feedback loop.
A runaway greenhouse effect, exactly. The planet got locked into a cycle where it couldn't cool down. The oceans boiled away completely. All the carbon was baked out of the rocks into the atmosphere, and the planet became a crushing, burning hellscape.
What's it like there now?
Today, the surface of Venus is 900 degrees Fahrenheit, hot enough to melt lead, with an atmospheric pressure 90 times that of Earth's, and clouds of sulfuric acid.
So Mars died of cold, and Venus died of heat. And Earth.
Earth was the survivor, the
Right.
Goldilocks planet. We were in just the right spot, not too close, not too far. We kept our magnetic field because we're big enough to keep our core hot. And we have plate tectonics, which is something the others lack. And that helps regulate our atmosphere by cycling carbon over geological timescales.
We really are walking a tightrope, aren't we? It makes you look at the blue sky a little differently, knowing how easily it could have gone wrong in either direction.
Absolutely. We are the beneficiaries of a very long and improbable series of fortunate events.
Before we wrap up, we have to mention the one sibling that didn't even get a chance to be a blue planet, the smallest one, Mercury. The outline calls it Mercury's scars.
Mercury is the weirdest of the bunch. It's a real puzzle.
It's like the avocado pit of the solar system, all core, no fruit.
That is a fantastic analogy, and it's completely accurate. Mercury is incredibly dense. It has this massive iron core that makes up about 85% of the planet's radius, and then just a very, very thin rocky mantle and crust on top. It looks like a planet that is missing its outside.
It's just the pit, so where is the rest of the avocado?
The leading theory, given all the violence we've been discussing, is that it was stolen, or rather, it was blasted away.
Another collision.
A massive hit and run. We think Mercury was once a much larger protoplanet, maybe twice its current size. It would have had a normal, thick mantle and crust like Earth or Venus.
Right.
But in that chaotic early period, it got hit by another planetary embryo, something large.
And the impact was just right, or just wrong.
It was likely a glancing blow, but it was violent enough to literally rip off the outer crust and mantle, blasting that lighter rock into space, but leaving the dense iron core relatively intact.
So Mercury is basically a planetary corpse. It's just the core that survived a murder attempt.
Exactly. It's a scar left over from that violent shooting gallery period. The debris from that collision was likely blown away by the solar wind or swept up by Venus and Earth over time, but Mercury was left as this dense, scorched little ball huddled next to the sun.
This entire deep dive has been a massive reality check. We started with that peaceful, static clockwork model, but the reality is...
What's terrifying? It is. We went from a collapsing gas cloud to a violent shooting gallery. We saw Jupiter bulldozing the inner solar system and stunting the growth of Mars. We saw Neptune getting kicked out and smashing into the Kuiper Belt like a wrecking ball.
And we saw the bombardment that, ironically, brought us our water.
Right, and then we saw the tragic end of the other blue planets. Mars lost its atmosphere to the cold. Venus was boiled alive by the heat.
And that is the big picture I want listeners to take away. The peace we experience today, this quiet, stable system. It's just a momentary balance. We're living in a quiet period, a stable era that follows an unbelievably chaotic youth. But when you look at Mercury, Mars, and Venus, you are seeing the scars of that history.
The source calls Earth a thriving oasis among dried-up deserts. And it really is.
It is. But I want to leave you with one final, slightly provocative thought to mull over.
Hit me.
We talked about how Venus died because the sun got brighter over billions of years.
Right.
The sun is still getting brighter. It hasn't stopped evolving. It's a fundamental part of its life cycle. It's about 10% brighter today than it was when the dinosaurs were alive.
Oh. The age of the Earth, our habitable period, will eventually end, just as the age of Venus did. As the sun continues to brighten over the next billion years or so, eventually, Earth will exit the habitable zone.
The oceans will boil here, too.
The oceans will boil here, too. It's our ultimate fate.
That is a dark thought to end on.
It is, but I think it's also a powerful reminder of our context.
Yeah.
We are witnesses to a specific, fleeting moment in cosmic time. We are here at the exact right moment to enjoy the oasis. Planetary balance is incredibly fragile. It didn't last for our neighbors, and eventually, far, far in the future, it won't last for us either.
Well, on that existential note, I think I'm going to go enjoy a glass of water, appreciate my magnetic field, and maybe put on some extra sunscreen.
A very wise choice. Enjoy the oasis while it lasts.
Thanks for listening to The Deep Dive. We'll see you next time.